Happy Wednesday. Welcome back. Let's see what we have today. So, last class we learned how you can systematically design sequential switches. Simple with them. But it was limited. It was just with a flop and very simple example. Today we're going to go a little more deeper, some more examples, because you need to have lots of examples for these kind of questions. They can be complicated, but it's a systematic way. If you do steps one by one, mostly you can get proper results. So what we're going to do today, we're going to do actually mostly we're going to do these steps that we started last class, from defining the problem and then drawing a state diagram, and then from that find a transition table, a Carnot map, and find the Boolean function, and then draw the circuit. These steps can be used for different circuits, can be used for different type of flip-flops. We can have two examples today. At the same time, we're going to do two examples. One is for traffic light. Or traffic light can be complicated, but here it's really just a simple traffic light. Traffic light that can switch between green, yellow, and red in each clock, going changing the color. But for red, stay 2 clocks red. Red is longer. This is the traffic light that we want to design today. Also, at the same time, we want to do one mealy machine structure when the output is a function of input and memory at the same time. That example, I'm going to explain that as well, is a sequence detector. Sequence detector is another circuit that when the input coming, if there is a specific pattern, it can detect it. Say, okay, is 0, 1, for example, 1, 0 is one pattern. It can detect. We're going to go for these two examples today, and do all of these steps one by one for these two. Okay, let's get started. Okay, so last class, we explained the first step is defining the problem. Problem definition. So problem definition means specify what is the input, what is the output, and do we have more, for example, is any clock there, is any reset input, is any, for example, illegal input? We need to consider all of these things. Sometimes we need to write them up. And or draw, for example, you can draw it. You can say, okay, this circuit acts as a block box. Like is that, for example, in this example, detect the sequence of 0, 1. Okay, detect of sequence of the 0, 1. This circuit called sequence detector. So for example, this input X can be so many things. It's just a sequential input that coming, like for example, 0, 1, 0, 0, 1, 0, and more, and coming one by one as a X. And this is a sequential circuit, so it has clock. And output is Z or Z. And this Z, if the pattern happening, like for example, the pattern is 0, 1 in this example. Okay? So if the pattern happen, so pattern happen where? Here. Yeah, here happen. Here happen too. So the result's going to be 0, 0, 1, 0, 0, 1, something like that. So the 0 means the pattern not happen, and 1 means the pattern happen. So this is what we want to design. This is also part of the definition of the circuit that we want to design with that picture, because one picture has lots of meaning in terms of explaining. You just can draw the picture. Picture is very important. Especially for our job that is designing a circuit, if you can draw that as a picture, that has lots of benefits. You can understand it much better. There is also, for example, reset as another input. It can be active low or active high. For example, here is active high. So if it's active high, we don't need to put this. For example, reset, another input. Okay. This part called problem definition, and you need to know like behavior of the system. We're going to do this example step by step. When I explain this step, at the same time, I do this example. What is the example? Detecting a sequence. Detecting a sequence can be complicated. Here is just 2-bit sequence. It can be 3, it can be 4 or more. The sequence is like a key. When you enter the key, and suddenly door get open. When the pattern happens. This is called sequence detector. So we want to design this circuit. Sequence. Okay, second step, after defining the problem, is to draw a state diagram. The state diagram is also visual. You can visually explain how we are moving from one state to another state. For the system, this is like a system that we want to design. Inside this system, we have some state. Why we need a state in this system? Why we need memory in this example? And we decided without any memory, the sequence detector. Any idea? Why we need memory? No, we can design it without memory. But why you what you think about it? Why you think we need a memory? Do we need to save something? Yes.
You need to save the previous bit.
Exactly. We need to save the previous bit. To see this sequence happening, we need to save it. If you don't know the previous one, how you can detect it? If it is more, if this is 2 bits, but if it's 3, probably you need to save 3 steps before, or 4 steps before. It depends the type of sequence that you want to detect. You need to save more, like previous patterns, previous bits. So for each bit, you need memory, of course. Thank you. Yeah. Okay, so that's why we need memory. That's why it has a clock. But what about diagram, a state diagram? We need to draw a state diagram. But if you want to design a state diagram or draw a state diagram, you need to know which kind of sequential circuit you are designing. Is it a Moore or Mealy? So Moore was the easiest one because in Moore, the output is just a function of a state. But in Mealy, the output is the function of state and input. That's a different. So, but the main difference is in Mealy, you don't need clock to get output. It can be faster. Even before receiving clock, you can make output ready. That's the main point. The state diagram for Mealy and Moore are different. Here, I'm going to explain them, okay? So first of all, let's go for this system. This system is complex. The sequence detector, it's a little complex. Even though it's just 2 bits, the state is not easy to understand. Let's see what states we have. The first state we can consider no match. Okay, so because we are detecting 0, 1, the state 0 is no match. No match happening if 0 coming. If 0 coming, we are staying in no match because nothing similar to this. This is the match. Happens. Okay, what about if 1 comes? If the 1 comes, we have 1 match. We have 1 match if 1 comes. So we can call that a state 2, state 1. Okay, here, if another 1 comes, we just can stay in that state. We're not going to change because another 1 is just another start. So we're going to stay again in the state 1. Okay, so here means 2 1s happens. Here is 1 1. We don't care about the past. We are starting from now. Imagine we are starting from. Oh, let's do this example that we already have here. Okay, so here's 0 come first, so it's turning. Then 1 coming here. Okay, if another 1 coming, we're gonna go back. If 0 coming, we're gonna go to another state that here is 2 match. So 2 match means good. Okay, so we call this state S2, state 2. In more design, in more method, we inside the state we also consider output. So here output is 0, here output is 0, here output is 1. Because here we detected the pattern. Pattern was 1, 0. So we detected. So we detected the pattern. So the output is 1. What about in this state? In this state, maybe another, maybe 1 coming. If 1 coming, we're going to come back to this. If 0 coming, we already detected, but we need to choose, we need to go to this state or that. That state means start from beginning. But if 1's coming, means we are already detected 1, 1. So we're going to come back to a state 1. So this diagram is a Moore diagram. If I tell you for this example, use the Moore method, you need to have this as a state diagram. And you have 3 states. State 0, no match. State 1, 1 match, and 2 match. What about I ask you draw Lily? Yes.
0, 1, or 1, 0?
Yes, this is for 0, 1. Yeah, I didn't get a chance to fix yours, so you fix it. It's 0, 1. It depends from which direction you look. The input I consider from this direction. So if in your slides you make it, I wrongly wrote it 1, 0, but it's 0, 1. So it means I start from this direction. So this is least significant bit, and this is most significant. Yeah. Any more questions? Okay. So we know what is the problem. We want to design this. We have some sequence coming in, clock, and in each clock, one of these inputs serially coming inside. And if first bit match, we're going to go to this state. If the second bit match, we're going to go to this state and print and make output. But the output is, right now we have 3 outputs, 0, 0, 1. As you can see, 0, 0, 1. Those 0, 0, 1 coming from this turning in this loop. Good? Okay. But this was something that we knew before. But right now I want to talk about melee. Imagine we want to design the melee part. In melee part, there is a little difference because in melee, input is also important. And we make output when the input comes right away. So we actually consider output here, for example, in this transition. Okay, so let's draw that. Clean this. Okay. So in melee, we have 1, consider state 0. State 0, no match. No match. No match means nothing is still similar to the sequence that we need to detect. Okay, if there is no match and 0 coming, we stay in no match because the sequence starts from 1, not 0. So 0 means it's still no match. Again, consider sequence 0, 1. In your slides, I wrote 1, 0. So you need to cover it. Okay. However, you can go with that too, but it's going to be different. This picture is going to be not similar. Here is going to be 0 instead of 1. But because I had these pictures, I wanted to follow that. Okay, so that's no match. That's similar. But when 0 coming, the output is also 0. So we consider output in the transition. So the output is also 0. Okay, so if we consider output right away, we might not need 3 states. We might do it with just 2. Let's see why. If 1 comes, what is the output? It's still 0. The output is still 0, but we go to another state. We call it S1. It's called 2 match. Okay? And the output is still 0. Okay, if here another 0 coming, another 1's coming, another 1's coming, we're going to stay here again. And again, output is 0. But if 0 coming, because we just print output right away, we don't need another state. If 0 coming, we can print 1 and go back to state 0. So the difference between this and that is, first, in the state we don't have output, we have output in transition. Yes?
If in state 0, do you need to track if there's a 0 and then if there's a 1? Because then if there is a 0, then there's a 1. You output 1 to Z. Because it says detect the sequence 0, 1.
Yes, you're right. Actually, good questions. So yes, so that's why we consider here no match. So imagine there is no match. We are in a state that is no match. Yes, if, for example, we start with a match, it means, for example, we start with this, we are already in a state 1 match. Okay, so a start, yes, important. Where we start? We started here because we started with no match. But if, for example, this is the sequence, start with this, you need to, for example, this is the sequence you want to detect. So in this case, a start is S1, means we already have one match. The first input, am I right? Actually, no, doesn't matter. You know, when we start from even here, well, yes, I think this covers both cases. Doesn't need even move to a state. A state 0, we can always start from a state 0. Let's see. We can just consider this as a start. Because in the state diagram, we also need to specify which state is a start state. We can start it with that. Why? Because whatever we're gonna start with something anyway. It's 0 or 1, and this gonna consider both cases. Did you get the point? It's gonna start, but it was a good question because yes, where we start, we need to specify start. In a state diagram, we always consider one state as a start. So a start can be S0 because it's here we consider it from 0 is start all the time. But if we didn't specify, you always consider S0 as a start. If I don't mention anything about it, S0 is a start. Okay, so in this case, this is a Mealy machine. We're going to go with this Mealy design because we did that before. We're going to go with this design because also simpler. Just have one. Okay, how many flip-flop we need in this? We have 2 states. With 1 bit, we can have 2 states. Here we have 3, so we need 2 bits. But in that case, we just need 1 flip-flop, just 1 bit. Because 1 bit showing 2 states, 0 and 1. So we need just 1 flip-flop, and that's simpler. Okay, we're going to go with this. If you want to write this up, because it's actually in lecture notes, but it's not in your lecture. Okay, good. So this is the second step. I need to clean this up. So the second step is a draw the diagram, more formally. States actually consider the memory of the past. We can label them with S1, S0, S1, and so forth. And it depends which method you are using for your sequential circuits. It can be Moore or Mealy. In Moore, we specify output inside the states. Like we have S0, the output is, for example, 0, 1. This is the output. And in Mealy, we have it in transition. If for example, is A coming, the output, we consider output here, output, S0 to S1. This is for melee machine. That's the difference between these two state diagram, melee and more. Good. Any question about this? Let's go to the next step. This was two first steps, explaining the problem, problem definition, and draw a state diagram. Drawing a state diagram is the main part. Without that, you can't go more because you didn't get the problem. That's very important. Okay. Next step. Oh, okay. Let's do it for another example. So we are in two states. Right now, we want to do this problem, this two steps for another problem. This problem is traffic light. Traffic light is also very famous problem that always you can actually use it in this case. Okay, let's see what is this problem. We want to define the problem. Problem is traffic light. Traffic light, normal traffic light has three lights. Green, it's stop. Yellow and red. Imagine in a lab you want to implement this problem with LEDs. You have three LEDs, you want to implement that. Okay, so that's what you want to design. You need to design a circuit, and this circuit, in problem definition, you need to specify inputs and outputs. So the output's gonna go for this, and is active high, so this part needs to connect to the ground. This is ground. So it means this is new. So in this case, this LED needs to be one to get light or get on. Okay, so we want to design this circuit. This circuit called traffic light, TL. What inputs we have? Do we need input for traffic lights? We can just do it by clock. So we just need clock. We need clock for sure. So we need clock. So we say, okay, each clock coming, these lights start flashing from green, become yellow or orange, and then red, and stay 2 clock red, because we want to make it a little complex. So stay 2 clock red, and then again turn back. So we don't need input. No input, any more input. But let's see, maybe here we consider, yes, we have another input for resetting. Active high. So we have another reset. This is also reset. So we have clock and reset as an input. That's it. This is the circuit we want to design. And this circuit called traffic light. HG, it's because this is for highway, for example, is highway green. So this can be HG green, HY, and HR. So the behavior is that first when it gets reset, start from green. And then in each state, when the clock coming, changing from green to red, and stay green to yellow and then red, and two consecutive clocks stay red, and then start turning. That's it. And the table also showing the steps: 1, green; step 2, yellow; step 3, red; step 4, again red, and repeat. Okay. So this table also showing how it's working. We sometimes call that behavioral table. But this picture also showing the same things as well, kind of. So we want to design that. Second step is to draw a state diagram. The state diagram here is more, it can be needed. Why? Why not needed? Any idea? We have input at all? Yes.
There's no.
No input. There is no input. No input. Why needed? Thank you. Yes. There is no input. If there is no input, those things, clock is not considered as an input. It's clock. Clock. We have it all the time. Reset is also not considered as an input. Because they are like a general inputs. But we don't have input, so we just go for more. We want to draw a state diagram. How many states we have? We can, okay, another thing, we might have different methods, you know. Maybe you go home and say, okay, what about I designed this with three states? It might be, I didn't think about that, but maybe if you have idea, go home and try to see if you can do it with 2 or 3 states. But to make it simple, I just made it 4 states. Because of this red that tried to stay 2 clocks red, I made it actually 4 states. The state 0 is when green is on, green. State 1 is yellow. We don't have input, we just have clock here. When the clock coming, we're gonna go to a state yellow. And if another clock coming, we're gonna go to a state 2, that is red 1. Another state coming, another clock coming. We're gonna go to another red. Oh wait. We're gonna go to another state 3, red 2, and then again, this is clock. This is clock. But this is a state diagram. A state diagram is very simple. It's like a counter. We did that last class. It's actually counter, kind of counter, because it's counting and becomes 0 when it keeps counting, and keep counting all the time to get reset again. So this is similar to the counter, but that's a state diagram. And transition happening because it's triggered by edge. Anytime edge coming, it's gonna change. But we have output. What is the output? Because we need to specify output in a state, we consider them with this. So when I'm mentioning green, means green is 1, and the rest are 0. So maybe I write that with another color. 1, 0, 0 is the output. 0, 1, 0, 0, 0, 1, and 0, 0, 1. So the output, so each bit is for, when I'm saying 3 bits output, this is for green, this is for yellow, and this is for red. Output. So we have 3 bits as output. Okay. We didn't mention, oh yes, in the picture also, in last picture, Here we have 3 output, as you can see. We have 3 outputs. Okay, good. So we have output. No. Any question about this? Let's go to another step. Another step is to find the binary codes for state and transition, a state transition table. A state transition table is very important. Binary code is important too, but it's easy. So binary code is not, you just can use normal binary code, but sometimes you can use one hot. One hot is also important. One hot means the output, the code that you are choosing based off the design. Sometimes you choose, okay, this is one code. Oh, just one hot. One hot means just one of them one. This is one hot, and then this, and then this. This means one hot. You can choose different type of coding, or even you can use gray code. One hot, if you use one hot, you need to have like you need to use 2 times more flip-flop. Because for actually showing 2 states, you need to have 2 flip-flop. If you use one hot, this is the one hot. One hot means just one of them is 1, the rest all 0. Okay, in this case, we just want to use binary. So if we use binary, for this example that we had, sequence detector, we just need 1 flip-flop, 1 bit. So, and what about transition table? Transition table showing how inputs, based off the input, output changing. So we have Q0 and input. This is the example with input. Remember, this is the input is the bits that coming that we want to detect a sequence. And the output is, because we just have 1 bit, so we just need 1 flip-flop. We call it Q0. So Q0 plus means next step. And we also have output. So for a state S0, because this is 2 inputs, so we have 0, 0, 0, 1, 1, 0, and 1, 1. 0, 0 is a state 0, and S1 and S1 is a state 1. Okay? What about output? If we are in 0 and 0 coming, we stay in the 0, and output is 0 based off the diagram. That's why I put that diagram there, because based off that state diagram, you need to draw this. Okay. If you are in a state 0 and 1 coming, if 1 coming, you're going to go to state 1, but output still is 0. If you are in a state 1 and 0 coming, you are in a state 1 and 0 coming, you're going to go to state 0 and print 1 as an output because you detected pattern. If you are in a state 1 and 1's coming, if you are in state 1 and 1 coming, you stay in a state 1 and the output is 0. In this picture, I think, yes, correct. Good. That's the important part. Showing how we change the state. How we change the state when clock coming and the input coming, we go to this state. Q become Q plus. This is called transition table. Draw transition table is an important part. Because from this transition table, we can draw Carnot map. We can find relationship between output and input. So we always have loop. We need to find this loop from output of register to input. And we can find that from transition table. Any question about that? Okay, this is step down. Let's do it for traffic lights. We want to do the same problem with traffic light. We want to draw the state diagram. So in traffic light, we had green, yellow, red, 2 reds, and we need 2 bits because it's 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. So for these states, inputs, we don't have more inputs, just Q, Q0, and Q1. So all the possibilities that they can have, we consider that a next step. Next step is when clock coming. When clock coming, we are going from green to yellow. So 0, 0 becomes 0, 1. From yellow, when clock coming, you go to red, 1, 0. And if you are in 1, 0, and clock coming, you go to red 2, 1, 1. And from 1, 1, if clock coming, going to go to 0. It's like a clock. It's like a counter. But you have output as well. But output is hot 1. Because one of them is hot all the time. So for green, green light is on. For yellow, yellow is on. And for red, red is on. You also can consider if you want to have reset, you can consider here as well. But reset can be done separately. So you can say, oh, if the reset is 1, we consider Q1, Q plus, and Q0 plus is equal to 0, 0. Also. Okay, so let's go for next step. Next step is finding the output. Finding the output is like finding the function, Boolean function. So for sequential detector, let's find the output here. How we find the output? We find we look at the table and find ones and find the function. So here we have 2, 1. So Q0 plus is equal to, we have this and this. Q0 plus bar I in plus Q0 I in, because it's all, these two are same, this is going to go I in. And Q, that's it. And what about out? Out is just here. I need to put them. Okay, and this is Q0 and in bar. That's it. We can make it easier. We can make it simpler. But this got simpler. I in and that. That's very actually simple. And then we can draw it as well. But we can draw it in a next step. Okay, let's do the problem with actually traffic light. In traffic light is very similar to the counter and the same output as counter. So for Q1, we have 2, 1 here. So and for Q0, we also have 2 1s here. So Q1 is corresponding to the D flip-flop and Q0, D0. Because we are using D flip-flop, we just put D0 and D1 instead of Q1 and Q0. It's the same because D flip-flop is just equal. Okay? So we have that as well. And let's go for drawing. We don't have time. Drawing is important. Let's do it first for this actually detector, a sequential detector. So we have one flip-flop. We use D flip-flop first. We can make it JK2. D flip-flop. This is Q0. 0 bar. And this is D. Okay? So the output, can we compute output later? First, Q0 plus is the input, is equal to I. We also have I. And so the I is connected to, and output, we need to negate that, go to the output, and also I0, Q0, another color. When it's passing another line, it's better to use. Okay, and this is out, and this is in. Yeah, I think we should just connect this to this. This is I. That's it. Even we don't need this part. That's it. So the output is Q0 and I bar, and Q0 plus, that is the input, is equal to I. It was very simple. If you want to design with another flip-flop, like JK flip-flop, we can do that too. But we're going to do next class. Don't worry about that. Let's do that just for this traffic light, and we finish it for today. So for this one, we have two flip-flop, D0 and D1. And this has Q0, this has Q1. Okay. So let's go for, this is two functions, D0 and D1. D0, let's change the color to another one. D0 is just Q0 bar. This is Q0 bar. Um, 0 bar goes to 0. Okay. And is that correct? And okay, and D1 is XOR D1 coming from here, and Q0 coming from here. That's it. That's this part, but the output is different. This is the output, green, yellow, and red. Another color for that. So for the output, we need to check here. So Q1 bar, Q1 bar, this is Q1 bar, or with Q0. This is for that. For this one, we have Q0 bar and Q1. And for this one, we have do another color for that. This one. This part is connected to the ground to turn that LEDs on because it's active high. Okay, that was a very simple example of sequential circuit. Next class, still we're gonna have more examples.